Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with differentiation, looking at stationary points and curve sketching. So if you're ready to learn, then let's get into it. So to start, stationary points is basically a point on a graph where our derivative or our gradient, dy by dx, is 0. And there are two basic types from this. You can either have a local maximum, so this local concavity where it's like the unhappy mouth, and it has a horizontal tangent at that point, or you can have a minimum, which is a local convexity. And this also has a horizontal tangent at that point. And for the maximum, this is where y prime, so dy by dx equals 0, and our d2y by dx squared, or y double prime, is less than 0. Whereas a minimum is for y prime equals 0, and y double prime is greater than 0. Another interesting point is the point of inflection, and this is where our y double prime equals 0, but y prime might not equal 0. So for our points of inflection, we'll have two main cases. This is where y prime equals 0, and this is known as a stationary point of inflection, and this is also known as a saddle point, or it's an inflection with horizontal tangent, and I'll show you the graph in a second. And then our other case is where y prime doesn't equal 0, and this is a non-stationary point of inflection. So here are three plots, and we'll go through each one. So on the far left, this will be a non-stationary point of inflection, so this is where y double prime equals 0, but our y prime does not equal 0. And we can have the opposite y prime, so it will be a negative gradient here. And so we'll have y double prime equaling 0, and y prime also not equaling 0, but this time it will be negative. And then on the far right is our stationary point of inflection, or our saddle point, and this will have both y prime and y double prime equaling 0. And as I was saying, this is our saddle point. If we consider the function y equals x squared x minus 1, we can work out where our stationary points are, or our points of inflection and things. So let's start with just finding the derivative. So y prime is equal to 3x squared minus 2x, and that means that our stationary points are going to be at x equals 0 and x equals 2/3, or that is to say 0, 0 and 2/3 minus 4/27. Those are the coordinates x, y. And so our y double prime is equal to just 6x minus 2. And so for these corresponding cases of x equals 0 and x equals 2/3, we have y double prime equaling minus 2 and plus 2. And these stationary points, I should have mentioned, is obviously when y prime equals 0 leads to these 2 points here, and so then leads to our understanding of y double prime. So as y double prime for this first x equals 0 point is negative, this is a maximum, and then this is positive, so it's a minimum. And we can also find our point of inflection, so y double prime equals 0 at x equals 2/6 or 1/3, and that's for the point 1/3 minus 2 over 27. So with all this information of our coordinates and whether it's a maximum or minimum and point of inflection, I should have said this is a point of Inflection. With all this information, we'll be able to draw our plot, and we'll go on to that in the next section, but I'll just show you the plot here now. So as you can see here on the right, we have our graph, and we have our maximum here at x equals 0, y equals 0. Then we have our minimum at 2/3 minus 4/27. Obviously this isn't necessarily to scale, but it's giving you a rough idea of what the plot will look like. And then we have our point of inflection here in between, where the gradient is, or the d2y by dx squared is 0, and our gradient is changing to go from our maximum to a minimum. And so this is the only sort of way this plot could work, given the information we have worked out from it. And in the next section, we'll be looking at how we can do this in more cases. When we wish to sketch a curve, it's useful to have a few arrows in our quiver, and we can start with a few techniques, and you want to memorize these to then put into practice when it comes time to sketch a curve. So for our first arrow, we have examine behaviors as x tends to 0, x tends to plus infinity, and x tends to minus infinity. And this will help us see where our graph may tend off to in any direction. Next would be looking for any symmetries, so whether the function's even or odd or anything like this. It will help us be able to just sort of copy and paste it onto the other side instead of having to go through the whole process again on the other side of the y-axis. Next, if our function y, f of x, is of the form p of x over q of x, where p and q are both polynomials, when p of x equals 0, this will be resulting in x-axis intersections, because the whole y of x will then be 0. Whereas when q of x is 0, we'd have y tending to infinity, and that will be a vertical asymptote, and that could be positive or negative infinity in the y direction. And finally, we want to consider any stationary points or points of inflection, i.e. what we've just been looking at. For the rest of this video, we'll be considering how we might want to plot this equation. So if you think you understand it, you needn't watch this bit, but I'll go through the whole process and show you how we come about drawing this equation. So we've got y equaling x times x minus 2 divided by x minus 3. And so for where it crosses the x-axis, so y equals 0, we would have x equaling 0 or 2. And then for small x, we'd have y being approximately equal to 2/3 of x. So now we might want to look at any vertical asymptotes we have. So for that q on the bottom, we're going to have when x is equal to 3, we're going to have y as being approximately equal to 3 over x minus 3. And as y tends to plus infinity, this will happen when x tends to 3, and we put a little plus up here to denote that this is from above, i.e. from numbers such as 5, 4 going down as we approach from above in x, and then y tends to minus infinity from below. So this is for x going through to minus, i.e. from below. So now, how does our function y look for large x, a large modulus of x? So we have our function x minus 2 divided by x minus 3. If we take a factor of x out of these brackets, then it will have x squared 1 minus 2 over x on top, divided by x 1 minus 3 over x on the bottom. And from here we can simplify it to be x times y 1 minus 2 over x times 1 minus 3 over x to the power of minus 1. And I'll let you do this as an exercise, but you can expand these and it will result in having x plus 1 plus order 1 over x, and that will be, therefore, as x tends to infinity, this will tend to 0, this order of 1 over x. So for x tending to plus or minus infinity, we have y tending to x plus 1, so it will have these straight line asymptotes of a y equals x graph but shifted up by 1. Finally, let's consider stationary points. So we have y prime equaling x squared minus 6x plus 6 divided by x minus 3 squared, and I'll let you prove that by using the quotient rule or product rule with a x minus 3 to the minus 1, however you want to do it. And from here we can find that x equals 3 plus or minus the square root of 3 for our stationary points. And if you wish to, you can then find the y double prime of both of these, but it's unnecessary because it can only really be one way around, so I'll draw it for you now. So we just start with our graph coordinates like this, where y and x are as normal. The first thing we might draw is our x equals 3 asymptote, which is for when x tends to 3, y tends to plus or minus infinity, so there must be this vertical asymptote around x equals 3. So let's write 3 to make sure we know what we're talking about. And then there'll be another asymptote which we found. For large x, we have y tending to this x plus 1 plot, so we wish to draw a y equals x graph, but then shift it up by 1 in the y direction. So maybe like this. And here I've drawn the coordinate axes not to scale, that's why the gradient isn't exactly 45 degrees, but you get the gist. And then from here, we also know that where the stationary points are, there's one at 3 minus root 3, so around here, and then 3 plus root 3 around here. And then, as I was saying, we don't really need to find y double dot, as it's quite obvious that this one above must be a minimum, and this one below must be a maximum. And the last bit of information we found is that for when y equals 0, it goes through 0, 0, and 0, 2. So when we wish to draw it, it can really only follow this shape, where it comes up and down through 2, that wasn't exactly right, and then like this. And that would be the shape of our graph if we got rid of all these lines that helped us draw it. It would end up looking like this. So using these methods, we can see we can get to this graph just systematically. Today, we've learnt about stationary points and curve sketching. In the next video, we'll be looking at the parametric representation of curves and polar coordinates. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.